Namaste and welcome back to the course on statistical mechanics of phases and phase transitions. In this lecture, we are going to continue our discussion of the one-dimensional Ising model. So let me quickly recap what we did. To solve the one-dimensional Ising model, we introduce a different set of variables than the spin variables that we usually work with. After solving the problem, we found that there is no non-analyticity of the free energy at any finite temperature. And therefore, since we start from very high temperature where there is no broken symmetry and so on, we concluded that there cannot be any phase transition as we come down in temperature at any finite temperature. And there was a puzzle as to how we recover the fully polarized magnetized state at zero temperature. We figured out that there are certain excitations in the 1D chain which are called domain wall excitations, and these excitations proliferate and they will destroy magnetization in the thermodynamic limit at any finite temperature, however small. Okay, and this is the reason why there is no finite temperature phase transition in the one-dimensional Ising model. Okay, what are we going to do in this lecture? In this lecture, we are going to introduce a very important tool in theoretical physics. It is called as the transfer matrix approach. I am going to introduce it in the context of the one-dimensional classical Ising model, but this transfer matrix approach has wide variety of applications from simple systems like Ising models to disordered systems and a variety of systems. So it's definitely worth exploring this and also learning some of these techniques so that you can use it in your own work. So we'll not only learn the transfer matrix approach, we will also gain some physical insights. As you will see, the outcome of this exercise of solving the one-dimensional Ising model again using transfer matrix method will also reveal to us certain physical insights which are interesting. Okay, so I have introduced some new terminology called as transfer matrix. So I have to prepare some background to introduce this. So let me do that. So to sort of make the explanation of this also and for your understanding a little easier, I am going to renumber my sites. So in the previous lecture, for example, we started numbering the lectures, we started numbering the sites from 0 on the left to 1 to all the way up to n minus 1 on the right. What we are going to do now is we are going to number the sites from 0 on the right, and this should be 1. It's not 2, it should be 1, and all the way going up to n minus 1, and then n equal to 0 will connect up to I equal to 0. Okay, so I'm going to number my sites from right to left rather than left to right. Okay, all right. Now what I'm going to do is just quickly revising that there are n spins with periodic boundary conditions, etc. We will get 2 to the n spin configurations. Now, if you look at the discussion we had in the last lecture, I had not applied any symmetry breaking field or any external magnetic field in that solution. So when I went to link variables, I had just the Ising Hamiltonian with no external fields. So the power of the transfer matrix is that it can also handle external fields in a very nice way. Okay, so I am going to introduce external fields in the simplest possible way, which is a homogeneous external field. Homogeneous meaning that the external field does not depend on which site it is acting. So it's acting same at all sites. So this H can now be thought of as a physical field that you are applying in the laboratory, or it can be thought of as a symmetry breaking field. So for example, I could think of applying a symmetry breaking field, solving the problem, and then taking the limit of the symmetry breaking field to taking the thermodynamic limit first and then taking the symmetry breaking field to 0. I could actually use this device to do that calculation. So when I impose periodic boundary conditions, of course, the spin at site n will become same as the spin at site 0. So site n is actually identified with site 0. Okay. To prepare for the transfer matrix calculation, I am going to rewrite this term slightly differently. So what I am going to do, I am going to take this h times Si associated with the site I and give half of it to each of the neighbors in a sense. So what I'm trying to say is that this term was written in terms of sites, sum over I Si. If you look at this way of writing it, where I have put a half and then I have just taken something like the average of spin or something like that, the way you think about this is that this is a term that lives on the link. So as you saw in the last lecture, Si plus 1 Si is some object that is living on the links. Similarly, Si plus 1 plus Si also can be thought of as a variable, that an object that is living on the links. So that is the idea of this, of writing it this way. So what you want to do is, you are trying to write the Hamiltonian purely in terms of things that live on the links. Okay. So you see that our preparation of link variables is already anticipating that, we are going to be doing something like transfer matrix. So when you start organizing things in terms of link variables, it is so this is why we also use the previous solution, so that we can understand why link variables become important. Okay, so now I'm going to write down the partition function. The partition function is a function of k and h tilde. Now what is this h tilde? So here, when I go to I had introduced this magnetic field, which is an energy scale. J is an energy scale, H is an energy scale. I now have two dimensionless coupling constants in this problem. Namely, there is J by T, J exchange by T, so that is a K, that is the dimensionless coupling constant. And H tilde is a dimensionless coupling constant, which is the energy associated with the magnetic field divided by temperature. Okay, so the partition function is now, I'm not writing as a sum, I'm not writing the Hamiltonian explicitly. What I'm doing is I'm taking the sum over all these terms and I'm exponentiating the sum, right? Exponential of a sum is product of the exponentials, and this is what I'm doing here. So I'm writing the e to the minus beta h term as product over all links. You must think of these as link variables now, and exponential of the energy associated with that link. That is the way you want to think about it. So if you put h tilde equal to 0, this would have been our mu variables that we had defined in the last lecture. So this is exactly the point I was making, that you should interpret these objects as terms associated with the link I. Okay, so if I think of this object as a term associated with link I, how many possible values can it take? It can take 4 possible values depending on what the values of Si plus 1 Si and Si are. Si plus 1 can take 2 values plus or minus 1. Si can take 2 values. So this object here can take 4 values. Okay. So the idea of the transfer matrix is to state that these 4 possible values of this quantity which is sitting associated with the link are elements of a matrix called the transfer matrix Ti that sits on the link I. So I'll repeat this. There are 4 possible values of this object here. Those 4 different values can be thought of as the elements of a matrix that sits on this link I. So you may wonder, how can 4 objects be made elements of a matrix? So instantly you realize that that should be some kind of 2 by 2 matrix. So how do we think about this? So if you remember in quantum mechanics, when you write a matrix, say you have a Hamiltonian and you want to write a Hamiltonian matrix, how will you find the matrix elements of the Hamiltonian matrix? What you would do is you would choose a basis of your Hilbert space and take inner products of the Hamiltonian, something like a bra, the Hamiltonian matrix and a ket. You will take these matrix elements, and that is how you will get the entries of the matrix. So what I am going to submit to you now is, imagine that at every site I have a 2-dimensional vector space spanned by Si. So remember, Si can be +1 or -1. So what is a natural way of thinking about these two states? The natural way of thinking about these two states are their eigenstates of some Pauli operator, Pauli Z operator, that is sitting at site I. So the idea is that at site I, you are just imagining that there is some 2-dimensional Hilbert space and there is a Pauli operator associated with that 2-dimensional Hilbert space. In fact, there is a Z Pauli operator with entries, diagonal entries 1 and -1, and the state Si equal to +1 is the +1 eigenvalued eigenstate of Zi, and -1 is the eigenstate of Zi with -1 eigenvalue. So I can imagine that there is a state here and that there is a matrix called as Ti, which is the transfer matrix associated with links, which will talk to the Hilbert space on both sides. So what do I mean by talk to? So this is the statement. So this state is at site I +1, Ti is the transfer matrix or transfer operator sitting on this link, and this is the state associated with this site. So now you see, when a Si goes from +-1 and Si +1 goes to +I +-1, you will get 4 values, and those 4 values can be organized in this fashion. Okay. So now when I have discussed this with students in the past, people would be slightly confused. People would wonder, we are discussing a classical problem, so what is this Hilbert space and where is this coming from and so on. I will point out to you later in the course that yes, this can actually be thought of as some physical thing, but for now you can just think of this as a device to perform this calculation, right? You can just imagine that there is these numbers here which are 4, which have 4 possible values. This expression here are elements of a matrix that sits on the link I, and the right side talks to the Hilbert space on the site I, and the left side talks to the Hilbert space on the left side, on the other side. Okay, so now we know what the matrix elements are. So what you do, you just take Si +1, put +1 here, Si +1 is +1, Si is equal to +1. You put that in this expression and you will get this as the matrix element, and that's just this formula where Si +1 is put as +1 and Si is also put as +1, and you can work out the other things, and this is Ti. Now the way we've set this up, this transfer matrix value will be the same for all links, the way we have set it up. So I want to emphasize here that you can actually generalize it to places where the system does not even have translational symmetry. Okay, this is important to emphasize, and that's why I mentioned about disorder problems and so on. Okay, so with this insight, you see that this expression here is the matrix element associated with the transfer matrix at site I. You see that you can rewrite the partition function as sum over all possible configurations of the spin. The first link will contribute this. So it's the transfer matrix element going from site 0 to site 1, and then from site 1 to site 2. So now you can see why it is also called as transfer matrix. So if you think of this as some kind of some sort of problem where something starts here and it moves and so on. It sort of transfers stuff from one state to the other. You will also see why we decided to number the sites in the way we had, because now you can see that this can be thought of in a nice way as matrix multiplication, which I will show you presently. So now first thing you observe is that if I look at a particular site I and sum over the two possible spin configurations at site I, this states will give you the identity operator. So if I sum over all these configurations except the last ones, except S0 and Sn, then I will sum over this S1, that will give me identity, so that will give me T0 times T1. And similarly, if I sum over S2, I will get T1, T2 and so on until I reach here. So what happens? This is first you hit T0 on S0, T1, T2, T and so on, and then all these starting from 0, you just keep multiplying these transfer matrices. Okay, and you reach Sn. But remember now that we have summed over all the spin configurations except at site 0 and site n. And therefore, I have gotten rid of all these intermediate states and I just have the product of the transfer matrices. And then what do I have finally? I use my periodic boundary conditions. I realize that Sn is same as S0. So what do I now have? I now have that the partition function is the sum of the matrix element over S0 of the product of all these transfer matrices. But suddenly you realize that when you sum over all this, I am taking the trace of the product of all these transfer matrices, and so my final answer for the partition function is a remarkably beautiful result, which tells me that the partition function is the trace over the product of transfer matrices multiplied around in this fashion. Okay. In the problem that we are discussing, each Ti is the same. It is the same matrix at every link because our problem has translational symmetry. So what this tells me is that the partition function is trace of T to the n, where T is the matrix that we derived in the last slide. So this is a remarkable result. So we have shown that we can derive the partition function by thinking of the link of objects that sit on the link and interpreting them as elements of some matrix that connects site I to site I plus 1. Okay. Again, we have done this for system with translational invariance, but you don't have to restrict to that. All right. So you may think, all right, we have done something, but how is it going to help us in actually doing some calculation? All right. So I start from this expression that we derived in the last slide, and I ask, how do I find this answer? So first thing you observe is that you can actually diagonalize T. So when you diagonalize T, you have to find some in this case, because everything is real, it's an orthogonal matrix, in general some unitary matrix which transforms this to some diagonal basis. So I'll save you the algebra, and I have done this myself. So I'm just going to quote the results. So if you wish to check this, you please pause the video and check the calculations yourself. So you will see that the eigenvalues, there are two of them. The first one is lambda 1, the other one is lambda 2, and they are both functions of k and h tilde. So this should be h tilde here. And you can see that there are two terms here. There is this cosh term and there is a sinh term and some other terms, exponentials here. And this unitary matrix is some kind of rotation by an angle theta by 2, and that angle theta is given by e to the minus 2k divided by sinh h tilde. So what is it that you should remember from this formula? You should remember two things from this formula, from this set of formulae. The first thing is that for any value of k and h tilde, this lambda 1 eigenvalue is always greater than lambda 2 eigenvalue, both are positive. Lambda 1 is always greater than lambda 2. This is the first observation. Second observation is when I set the magnetic field going to 0, I will see that tan theta will diverge, and that is another way of saying that in the absence of a magnetic field, theta is equal to pi by 2. Okay. Alright. So now this expression is extremely simple now. So once I have t to the n, once I diagonalize this, I go to the diagonal basis, and you know the trace is independent of such rotations, etc. So the trace of t to the n is simply lambda 1 to the power n plus lambda 2 to the power n. Okay. Now I want to take thermodynamic limit. So I have to run n going to infinity. And here is where my comment about lambda 1 is always being greater than lambda 2 comes to play. So I can take this expression, pull out lambda 1 to the n and rewrite this in this fashion, and when I run n going to infinity, I will see that this is a number less than 1. Therefore, when I exponentiate that, when I raise it to the power of n and run n going to infinity, that will die, and so the answer will be essentially lambda 1 to the power n. Okay. So now you will say we have got an expression for the partition function with the magnetic field on, and now we will try to extract some physics out of this. What can we learn from this calculation? Alright, so since I found the expression for the partition function, from here I can find the free energy per site, which turns out to be this nice expression that is there, right? So it's T times log, etc. So our first step is to check whether if I turn off the magnetic field, do I get the same answer? Let's do that. So when I turn off the magnetic field, cos h by t becomes 1. So this term becomes identity. This term vanishes, so this whole term is gone, and I get e to the minus 2j by t, which when I take a square root will become e to the minus j by t. So the answer will be e to the j by t plus e to the minus j by t, which is 2 cos j by t, and that is exactly the result which we had derived in the previous lecture without the transfer matrix, using just link variables. So we have recovered the same result, but now we also have the magnetic field, which we can use to extract some interesting physics. So once I have this free energy, I can compute the magnetization per site, and so that is just done from this thermodynamic relation, and a little bit of algebra will show you that this is the expression. Okay, so what does this expression mean? So the interesting physics comes is that when you explore this, suppose you keep some finite temperature T greater than 0 and let the magnetic field go to 0. Then you will see at a finite t, since h by t will go to 0, the denominator will go to 0 here, and this is well nicely controlled, and you will just get 1 here, and you will get a 0 answer. So if you keep the temperature fixed and take the magnetic field going to 0, I see that there is no spontaneous magnetization. In the limit of magnetic field going to 0, the magnetization vanishes at any finite temperature. Now you play a slightly different game. You want to find out what is the magnetization at 0 temperature. So what you do, you play the game of the symmetry breaking field idea. So how do we do this? You first let t going to 0, keeping the magnetic field at a small positive value, and then run the magnetic field to 0. And now you can show, this is a little bit of algebra but not too difficult, you can just do it right here if you just pause the video. You will see that that will go to 1. So now we have recovered the result that at 0 temperature, if I keep the symmetry breaking field on, take the thermodynamic limit and then run the symmetry field breaking field to go to 0, I will a positive +1 value of magnetization will survive. Okay, as an exercise you can also do what happens if you take 0 minus, and you will see that this will turn out to be -1. Not very surprising, but interesting to check. Okay, very nice. So now we can go a little further and we can compute the susceptibility, which is simply the second derivative of this quantity, or you can think of it as the derivative of magnetization, and typically we work with zero field susceptibility. So we have to run h to 0 here. And if you work this out, you will see that I will get an expression like this as an exact expression. And what is the physics content of this? So you see that when t goes to 0, the exponent here diverges, and this fellow is exponential of 2j by t. So this whole thing diverges in a very fast fashion as you go towards t going to 0. What happens when t is much greater than j? Then this object here, e to the j by t, that goes to 0 and exponential of 0 goes to 1. So essentially I will get susceptibility goes as 1 by temperature, which is the familiar and celebrated Curie law. So we recover the Curie law at high temperatures, and at low temperature the susceptibility is much higher than the Curie value. It sort of exponentially blows up as you go towards t equal to 0. So you should pause and figure out why is it doing that. So let me give you a small hint on that for you to think about how to rationalize this result. So remember that in the last meeting we discovered that domain wall excitations are 4j above the ground state. Suppose I have a magnetic field on in the up direction, in the plus direction. Then if I create a bunch of downspins, the downspin's energy will cost a lot, right? Because it will cost 2h energy to flip a spin down. So if I have a domain wall and the domain size is some length L, then it will cost 2 times L times h amount of energy. So now you see any domain wall configuration is not degenerate with any other domain wall configuration with 2 link variables mu equal to -1. They will not be degenerate. Because of this, the entropy gain in forming domain walls will not be there, and therefore if I apply a magnetic field, I will want to really align with the magnetic field in a very severe way, if you wish. And this effect is accentuated as temperature goes to 0, and this is why you have this kind of very large susceptibility at low temperatures. Okay. All right. So it turns out that we can extract many more things from the transfer matrix. Let me show you at least one of them to convince you that it is really worth exploring this. So remember, for example, I had talked about the Kubo formula of response and so on. In those formulae, for example, I needed something like a spin-spin correlation function to find some kind of non-local susceptibility. So for example, I could go and say, suppose I apply magnetic field at some particular site, what will be the magnetization at another site? I could ask this question, and for that I will need this quantity. So remember, delta S is the S object minus the average or the expectation value of SI. It's the fluctuation in this quantity SI. Okay. Now what I'm going to do is I'm going to extract the expectation value of SI from the transfer matrix. Okay. So this might be a bit of a busy slide, so I'll just walk you through it slowly. So the expectation value of Si is sum over all configurations. These are the weights associated with the link. I am still working in the spin variables here. And what do I have to do? I have to put Si at this place. That is the object I am wanting to find the average value of. So I put that in the numerator and divide it by the partition function. All standard. Okay, now I make a key observation. I observe that Si can be thought of as the expectation value of these states of the Pauli Z operator located at site I. That is just saying that Si can be thought of as the eigenvalue associated with the state Si. So if it is +1, it is associated with the plus state. If it is -1, it is associated with the minus state. Okay, this is very interesting. Now when I sum over all the Si configurations, what will happen is I will get I transfer matrices here. I will get this Pauli spin operator sitting here and then T to the n-1 here, n-I here. You see what happened? I just snuck in a Z operator between the transfer matrices. So now by cyclic invariance of trace, I can move all of these operators to this side, and so that will give me T to the n, and I will get T to the n times Z. Now Z, remember, is just the Pauli Z matrix. So now what I can do is I can simply diagonalize T, and so that will give me lambda to the n, and remember there will be these U's, these unitaries that hang around. So I will get those unitaries and I will be able to write an expression like this. Once I have this, I will then be able to do an explicit calculation. I have U, which I derived in the last couple of slides back. I will be able to do an explicit calculation and show you that the numerator looks like this. So all I get is cosine theta. So when I now take the thermodynamic limit, this term, the contribution from this term will go away, and I will see that it's just lambda 1 to the n divided by lambda 1 to the n, and they will just cancel and give me identity, and the answer is cosine theta. And remember, when the magnetic field goes to 0, theta goes to pi by 2, and therefore the expectation value of the spin will go to 0. So the result that I had derived using thermodynamic free energy, I have actually again re-derived it for you using an explicit calculation of an expectation value in the partition function, and this is done using the transfer matrix trick. So all that happens is when I want expectation value of Si, in the position of in the ith position, I should insert, if you wish, a Z matrix, the Pauli Z matrix. And this gives me that the system does not have any spontaneous magnetization at any finite temperature. I recover that same result from this calculation. Okay, so you may wonder, hey, I had advertised calculation of correlation functions between spin I and spin j, so why not, where is that? Okay, here it comes. So since Si expectation value is 0, delta Si is same as Si, and therefore the correlation of fluctuations is simply the correlation of the objects themselves, because the mean values are 0. Okay, how do we compute this? The same arguments I used in the last slide to evaluate expectation value of Si, you can use the very same arguments to compute expectation value of Si Sj. So what happens here is, suppose I is greater than j, you will get j transfer matrices, the Zj operator, which as a matrix is just 1 minus 1 in the diagonals. Then there will be a bunch of transfer matrices. How many of them will be there? I minus j, I have assumed I is greater than or equal to j. And then there will be Zi corresponding to the ith site, and then there will be n minus I of them remaining. So you can see, if you add all this, you will get n transfer matrices, and I encourage you to work out the details. You will be able to show that if I take I minus j is some integer n, after some algebra with these U matrices and all of that, you will see that Si Sj expectation value is lambda 2 evaluated at h equal to 0 divided by lambda 1, this is lambda 1 not lambda I, lambda 1 when I minus j is n. So you will see that it is lambda 2 by lambda 1 to the power n. Now when the magnetic field is 0, you can show that this lambda 2 by lambda 1 is something like the tangent hyperbolic k. Now any number to the power n can be exponentiated in this following fashion, right? So you can exponentiate this and write e to the minus n by c. And what I have done here is I have introduced a quantity called a. What is a? Imagine that the physical distance between site I and I plus 1 is a. So it is called the lattice parameter. So I can introduce a coordinate between site I and j for site I. The position of xi, the site I is I times a. And what I do is I simply multiply and divide by a, and therefore I have to have something of dimension, and so that is distance between xi and j, and c is a new length scale that has shown up in the problem, and this is called as the correlation length. So what I have shown you is that the spin at site I and site j, their correlation is controlled by a new length scale that emerges in the system. What is this length scale? That length scale is lattice constant, which we just introduced here, divided by log cot h j by t. So let's understand what this is. Let's start at very high temperatures. At very high temperatures, j by t will go to 0. So cot h of 0 will diverge, so log of that will diverge, and c will go to 0. What is this statement? The statement is that if I am at very large temperatures, a spin here is essentially uncorrelated with any other spin far away, and the correlation length goes to 0. That means every spin is doing whatever it likes to do and not correlated with other spins. So this is the result that we fully understand from a physical perspective, right? So the message is that a length scale emerges in the Ising model, and this length scale goes to 0 as t goes to infinity. What happens when t goes to 0? Let's see what happens when t goes to 0. When t goes to 0, this quantity diverges, that is j by t goes to infinity. Cot h of j by t will go to unity, goes towards 1. So log of unity will go to 0, and therefore c diverges. So as I am going towards 0 temperature, I see that this length scale, the correlation length starts to diverge. This is telling me that it wants to become like a ferromagnet. It says that okay, I should be if I'm a spin here, I should be correlated by someone I should be correlated with someone very far away. So this is indicating that it wants to become a ferromagnet. It wants to become an up polarized state. Okay, so you can see that the transfer matrix method allows you to calculate variety of things. You can calculate, you should explore possibly 3 spin correlations. You can explore variety of things, and you can see that this offers many opportunities to explore different aspects of the problem. Okay, so we have done a few things today. So let me summarize what we have done. We explored the transfer matrix method, and we solved the Ising model in one dimension using the transfer matrix method. We confirmed that we do not have a finite temperature phase transition. We found that there is a broken symmetry phase at 0 temperature, and most importantly, we learned that when I have a lot of degrees of freedom that interact with each other at some temperature, you can have new emergent scales. So in particular, the correlation length that we have is a scale that emerged from all these different interactions that you have. Okay, and this is a very important idea, and it will be a recurrent theme throughout the discussions that we'll be having. Okay, so this is what I have to say about the one-dimensionalizing model, and I'm sure that you are now very keen to know what happens in 2 dimensions. And I look forward to seeing you in the next lecture. Thank you and namaste.